before the 5-day lectures, I think it's better to talk about how we are going to deal with the data when we doing the NDE. Instead of looking at the signal processing techniques that everybody can see in other undergraduate or graduate level classes, for example, what you learn for time domain, frequency domain, signal processing, like filtering techniques, like Fourier transform, um, and so on, that it's better to look at more in how to understand what we're getting in the data when we're dealing with measurement. So the data we are getting for NDE, it's intrinsically noisy, and not only being noisy, it's going to have a lot of uncertainties associated with the entire NDE measurement process. So what is uncertainty? So let's first understand that by simply looking at a, a plot that I can draw here on the board. Let me do that. As I mentioned in the morning, that we are looking at from a system perspective. So I'm going to draw this on this. Sorry about the underlying text. So I am going to look at a problem where I have the system, output as my NDE measurement, right? So let's call the y-axis as my measure data. Measure data, right? So this data can come from any NDE physics, right? Electromagnetic, ultrasonics, and so on. Well, my input is the actual physical quantity I'm trying to measure using my techniques, right? So these are the physical quantity. Or physical variable, okay? Well, you'll see why I call this as a physical variable very soon. So if I have an ideal measurement technique, if I know exactly what I'm measuring and I made no mistake in my measuring process, what do you expect to get? Do you guys think? I am going to get a perfect 45-degree string line, right? So this is ideal case. But in the reality, it's not like that. Well, in the reality, what we're getting, well, you say, okay, because I may have some noise, I am not going to get exactly a string line. So what I'm going to get is something like this, right? Well, hopefully that I'm getting those measurement data point in this way, right? This is usually what you see, and in statistics, right? And you said, okay, this is what I'm going to measure in the real physical measuring process, and I can use linear regression to estimate, right? So what is the relationship between the measured data and the actual physical quantity or variable I'm trying to measure? Well, what's going on here, right? So why it is scattered like this? Well, let's try to break this into a few key concepts in measurement and measurement uncertainty. So let me give a few examples here. What happens if I'm having a measurement? Well, I have a measurement that I have a perfect relationship, something like this. So this is my measurement number one. So what is going on here? Well, if you have answer, you can try to type in. You can speak up. Maybe typing is better. You don't have to unmute yourself. So what I'm having here, well, I have a perfect linear relationship between measurement data and physical variables. Sometimes I may have the measurement is something like this. Oh, I'm sorry. No, I should do this. Right. Well, I don't have a scatter data point. What I have is a linear relationship here. But what's the reason? Because you can look at the discrepancy here, right? What's the reason for it? Well, one possible reason is actually I am having some systematic error, and although I have a perfect linear relationship, but there's some error between, right? Okay, so this is one thing, and let's not define it right now. Well, let's look at another way that I may have to get the data. Let me use a different color. So I may have some data like this, right? And for each physical quantity, I'm going to get a scatter measurement along the y-axis. That's also possible, right? Well, what is going on here? Well, for the first case that you have a systematic error, well, sometimes you also call this a noise or systematic noise. What is the knowledge of this? Well, sometimes you don't know what caused this, but if you know, you can easily compensate that, right? You can easily compensate it with that knowledge of either this is actually shifted in the measured data by a delta y, or this is delta y, or in this is just nothing but a delta angle, right? When you have these scatters, which means that, well, I have a perfect knowledge of what I'm measuring, right? And I know everything here is going to be aligned along the exactly value of this physical variable, but I am having a distribution of the measurement data point along the line. So what might be the reasons of having this kind of distribution there? Any thoughts? Well, this might be due to your NDE instrument, or it might due to the way you are actually doing your sampling and through your data acquisition, right? So it's possible that you don't have a fully understanding or have all the knowledge along this axis. Well, let me make this figure a little bit more complex. Let me see. Okay, I'm gonna have this pink color showing now I am going to not only have a distribution along the y-axis, I have my data also going to have a distribution along the vertical axis.
Hello.
Yes.
Yeah. Dr. Ming, there's an option of using whiteboard too in WebEx.
Okay.
So if in case you need it, so that could be a bit handy in that case.
Yeah, sure. I'm trying to see where I can open whiteboard. Do you know how can I open whiteboard?
Just give me 1 second.
Yeah, I don't see that option.
Now, in just next to where there's an option of end meeting or closed meeting, three dots are there, which says more options.
More? Yeah.
Just if you click on that more options, so the last option is start a new whiteboard.
Um, can you see my screen? Actually, I don't
Yeah.
see it. My options here like Q&A, captions, notes, polling, mute options. I don't see a whiteboard option here. Anyway, maybe we can also do one thing. I can add a blank slide and join there.
Uh, are you able to see that option of cross?
No, I can't. I cannot.
Just next to that cross, there is three dots available there. Bottom most options are there.
Interesting. I don't see an option. Maybe we can talk offline after that,
Yeah,
or
we'll
maybe you
talk
can give me a
offline and then we'll
screenshot.
synchronize.
Yeah.
Yeah.
Yes, maybe you can give me a screenshot. But anyway,
Yes.
yeah, sorry about this messy here, but I'm about to convey my idea here that for those distribution along the vertical axis and horizontal axis, you can see that it's corresponding to different sources of uncertainty. Okay, I haven't actually defined the uncertainty yet, but the uncertainty is basically due to the lack of knowledge in each component of the measurement process. And for NDE, of course, we are dealing with different NDE physics. So for the y-axis, the distribution there, as I just mentioned, it's due to, for example, the measurement tool. It's due to the data acquisitions, for example, the sampling strategy, and so on. And for the pink distribution here, this is due to the lack of knowledge of the two physical quantity that you are measuring, because sometimes you don't know exactly the two physical quantity. So you will have to assume it's going to have a distribution or associated uncertainties there. Well, the first thing I mentioned is a little bit easier. That's due to the systematic error, that it's easy to be compensated when you know the knowledge of that, right? So when you talk about the entire measurement process, the uncertainty coming from multiple sources that are going to identify for NDE problems specifically. This is an ongoing research topic that my group is doing. And this is actually critical, and you'll see that why we want to understand and quantify the uncertainties for NDE measurement. So we can achieve a true multimodality and multi-stage NDE data fusion, which is the foundation of the NDE 4.0 and 5.0. Okay, so this is a fundamental explanation of uncertainties. So let me clean this. All right. Okay. So the overarching goals of uncertainty quantification in the that how you want to quantify the uncertainties when we're doing NDE. Again, let's try to understand this from a fundamental way. Well, what do you mean quantification of uncertainties? Well, from the previous sketch plot, there's one thing that probably we can, try to hypothesize before we move forward is, if we know the way that those data plots or measured data to quantify how that is scattered mathematically, then there might be a way to quantify it. Or let me try to make it more simplified, is if we know the distribution of the data along each axis, along each dimension that we are looking at the data, then we can quantify uncertainty. Simply speaking, if we know the probability density function of the data, right, that's a perfect way of quantifying uncertainty. But that's, although a very simplified understanding of quantification of uncertainty, but that's a very challenging way either, because sometimes you really don't know the distribution, right? Well, how we can get a distribution? Well, statistically, there's one way of doing it. That is called, likelihood. Okay, so the meaning of likelihood is you are going to look at the data, and it's a data-driven process, and you are going to find the corresponding distribution with parameters to be determined. Okay, so that's one way of looking at it. Then there are different statistical techniques you can use to do the likelihood calculation. All right, so I'll stop here for the fundamentals, and let's move this to the real examples. So in terms of NDE, that there are three overarching goals that I identified here that UQ is important. How to do it? One is you want to categorize the noise. Well, now the noise here is going to have more meaning than what you probably have thought when we introduce the signal equation, talk about the forward inverse problem. It has intrinsic data uncertainty associated with it. And we need to have a systematic investigation of that uncertainty so we can better categorize the noise. Well, the second is we are hoping to get a multi-stage model from which we can actually discover the uncertainty over the entire life cycle of the material, which means that the uncertainties will be different at different stage. And we want to form the uncertainty quantification through an integrated forward and backward model. The last is it should be holistic. It should incorporate the randomness in the whole process, from data to model to discretization, or discretization here can be exchangeably use the term of simulation to machine learning. So each stage will have its own uncertainty quantification problem. So in day 5, I'll explain this in more detail. All right. Clean this. Let me use one example to further define the new research area of sciences in NDE and uncertainty quantifications through microstructure study. Well, I have to define this so the uncertainty quantification has more definite meanings, because it may mean different things for different NDE problems. So for a microstructure characterization, or for us to understand the materials at a micro scale level, for example, one challenging problem is the early stage damage detection and characterization. Instead of looking at the damage in the macro form, The macroform means it actually forms unmeasurable defects. Well, that's an easy problem, right? Although there are still a lot of work going on in ND domain, people say, okay, I want to detect the defects at different length scale. Let's say, for bridge, I'm looking at a defect at centimeter scale. For some component for the printed circuit boards, I'm looking at a defect at a micrometer level. But if we can quantify and categorize the damage before it reaches to the macro crack form, it is more critical. It's more important, but also very challenging. So that's how we can define early stage damage state awareness and characterization. Well, we can have different ways of doing it, and how have we understand uncertainty associated with that is critical. The second is the inversion of any measurements for material state awareness from a nano micro scale to meso scale and macro engineering scale structures, which means this will be a multi-scale understanding and uncertainties at different scale, how they will be propagated through different scales. That's also a challenging problem. The third is interrupted data collection. I think this is always a problem for measurement or metrology people, that we always have interrupted data collection. Sometimes we have limited data. Well, that's always true, right? Due to different reasons that we can have the data corrupted along the temporal axis or along the spatial axis. So how we can accommodate that and convert that into a function of life percentage of a material structure for this particular domain. The fourth is life cycle prediction and reuse management of materials. And UQ can be really useful, so it can provide more realistic probabilities of failure after we consider uncertainties respecting the evolution of material microstructures. The last is it will provide qualitative and quantitative feedback to the advanced manufacturing process for specific missions and expect life cycle durations if we understand uncertainty quantification problem. Let me give you one framework that I defined, and I call this D3M3. It's a little bit long, but I think if you understand each component of it, then it's actually you feel it's making sense. So I call this a learning-based computational mathematical framework for 3D dynamic data-driven. So it's a data-driven process, and it's a dynamic process, change over time. And 3M, multi-physics, multi-scale, and modeling-based UQ. How to understand this? Let's look at this framework. And I have a red circle here. Then I have 4 key components. Data. And for any problem here, I just pick, for example, ultrasonic and electromagnetic. It can be more. Model. And model here, you can have physics model, studying the interaction of, for example, the energy with multi-scale damage. The fourth is imaging and simulation. This is what we focus on in this particular course, and how we can deal with the data, how we can inform images using inverse problems, inversion techniques, and through imaging and simulation, we can take advantage of the data to do the accommodation of interrupted data collection, and we can also understand the MSA and damage evolution. Well, another important piece here, also this is a buzzword, although machine learning has been there since 1950s, but it has been revived due to the advancement of computational technologies and in computing hardware and software, right? So how we can use learning, particularly here means machine learning, to understand the characterization at different scales um, and try to do management and prediction of the entire system. Well, you'll see uncertainties in each aspect of it. Let me explain this briefly. For data, you have data uncertainties, right? When you do the measurement, just like what you are looking at the y-axis of the plot I show, you're going to have a data variation there. For the model, you're also going to have uncertainties. Why is that? Think about the numerical model you developed to understand the physics process. People always say all models are wrong. So why models are wrong? Although it's useful after validation. Well, that is actually a way to explain uncertainties when you actually establish a model. You don't know exactly the parameters, right? You don't know exactly. So most of the time, you'll probably do a study, say, hey, I'm going to assign the range of the parameters to this to start with. I'm going to guess, and I try to see if I can, validate the models through the experimental validation. Well, that's due to the uncertainty associated with the model. Well, for the imaging and simulation, you also have uncertainties there when you do the reconstruction, when you do the imaging to form the data, you don't have fully understanding of it, right? And the interrupted data collection is one example of it, that you don't know or the full picture. You only have limited data collected. Well, for machine learning, the uncertainty is also obvious. Um, well, think about one, popular way of doing machine learning. People like to use neural networks, right? And developed into a different way of doing neural networks, right? Let's say deep neural networks. Well, are you comfortable using neural networks? And people say, hey, I'm definitely a big fan of neural networks, right? As long as I have, you know, good training data set, I can have a neural network works very well. And that's true. You see that successful stories in a lot of applications. Um, let's name a few. For example, image recognition. When we talk about the ImageNet data set for autonomous driving, well, still people are debating now they're going to actually be happening very soon or not. But still, it has quite success. But what are the uncertainties there? Well, first of all, there's no perfect training data set, right? Also, it appears more like a black box to you, although you can have different way of model there, and you can have different way of construct the architecture of the model, but still, you don't have fully understanding what's really going on there. Right, so there are some ongoing research and published papers from my group talking about learning uncertainties, and if you're interested, you can read that. Okay, so outside of this red box, what we can achieve using this holistic onset quantification, um, so we can have a better understanding of the
So,
multi-physics, multi-scale. Yes.
yeah, I was just thinking that, like when ma'am was discussing about the forward problems, so we have a defect and we pass it through. We have a source and we have a known defect, and we collect the sample or we collect the signal, and that signal can be used for to say can be used as a testing signal for the neural network, and can we predict the defect profile from that signals? If we have a variety of signals, can it be done, or somebody has done that type of thing?
Oh yeah, that can be done. That has been done for many years. So let me, good question. Let me repeat what you just asked. Is I have let's say I have a sample. I have a defect in that, right? I choose an ND technique. Using forward problem, I get my measure data. From that measure data, I want to do data inversion, right? Inverse problem here. Well, you don't have to use a neural network. You can use other techniques, try to reconstruct the defect profile and estimate the size or shape or whatever characteristic of it. Or you can use the measured data as a training data set. Then you can use that training data set to train your neural network. So the neural network will give you, let's say, the output. And that can be done for defect profiling. And I think Michigan State, I think Professor Woodpie is the pioneer of doing that in the 1980s, 1990s, using neural network to do inverse problem for defect profiling. Well, but that can be done, but we are now looking at this from a different way, or maybe let's revisit this problem. What is the problem there? Well, I have my training data set coming from my forward problem. And the data either getting from experimental measurement or from simulation, right? But that data you are getting, first of all, it has its uncertainties, right? In the model prediction, it's not going to be exactly you know this what are exactly what we are getting or hoping to get, right? Because the model is not 100% accurate. Well, for external measurement, you also have noise, right? People like to use the term noise, but it actually have uncertainties with it. So with that uncertainties in the training data set, let's say you choose neural network or direct inversion, whatever, then your reconstruct defect is not going to be perfect. That's why when you look at the reconstruction, for example, defect profiling here or categorization of defect here, there's always going to be an error term there, correct? You'll say, okay, I'm doing this like 97%, or I only have 3% error. I think this is good. But how to understand the associated 3% error? Where does it come from? Let's say if I want to, there's some problems 3% is acceptable. Sometimes some application 0.3% is acceptable. 3% is too large. And you need to understand that from the fundamentals and quantify the uncertainties and try to reduce uncertainties. And that's the reason we want to understand this concept. You can combine everything into a noise term. You can combine everything into uncertainty term and only look at it as a compounded term. That is okay for some applications, but it's not going to be okay, I would say most of the time when we're dealing with the data. I hope I answer your question, and also on top of that, I'm trying to explain why we are here.
Yeah, perfectly.
Yes, great. So now when we have this in the left arm of this UQ, and you can see from this UQ that I can have the new sciences from NDE plus UQ. So it's not just we are getting some measured data and process the data. We actually understand what's this data acquisition process going on, or this measurement is going on statistically. Then we can actually then we can further help us to better understanding and give feedback to the manufacturing and the material qualification process. And this is going to be a closed loop, like a feedback loop type of structure here. Okay, so I will go to now a few key elements. Those are slides I work with my PhD students, so I want to give credits to them for each of them. And this is more like a tutorial since we're having this as a lecture, right? So I'll try to go to the basics as much as possible. So stop me if you have any questions. The first is type of uncertainties. So we can classify the uncertainties in two basic categories. One is called aleatoric uncertainty. So that's uncertainty arising from the natural stochasticity of observations. And it cannot be reduced even when more data is provided. Or in other words, that the uncertainties we call aleatoric, that's intrinsic randomness of the problem, for example, in the materials, that it has its own randomness. So those uncertainties that we cannot reduce even we have more data because their randomness is always there. The second uncertainty is called epistemic uncertainty. It describes, for example, it's more model related or describe what the model does not know because the training data was not appropriate. So due to limited data and knowledge that we have to deal with that uncertainty when we do the data collection and when we try to have a model explain it, when we have actually a learning process, then you have that uncertainties. And the good news is that uncertainty can be reduced when you have more knowledge, more data, so that can reduced over that mitigation strategy. Well, you'll see that there will be input-dependent uncertainties. There will be hidden variables or measurement errors associated with the aleatoric. And if you have not sufficient data, then you may have epistemic uncertainty there. Okay, well, for NDE problems, we would like to divide them into four major categories. Well, when I explain this, it's a table with a lot of text here, but I would like my students to think about an actual NDE measurement or NDE problem, right? We can pick one example. So let's pick maybe an example that we do on a daily basis. I don't know, anybody want to name one? I'm fine with that. Any example you picked. Let's pick one. So let's give 5 seconds if anybody want to name one that we can start from that. And any problem you want to explain based on that. If no, I will pick one. Okay, let's pick one. Oh, okay, I heard something.
No, anyone you pick, no issues.
Okay, let me pick one. Let me pick, let's say, how about the pipeline inspection? Okay, so I have a pig instrument. Let's say I use ultrasonics or magnetic flux leakage moving inside a pipe. So think about that scenario, right? I have that tool moving in the pipe and collect the data. The data is, of course, I would call this adequate, good quality data, right? It's not going to be way off. It's still good quality data, but the data interpretation of that is going to consider uncertainties, right? So what are the uncertainty sources in that particular measurement? One is a geometric uncertainty. The size of flaw in the pipeline going to be different. Well, you're going to have different type of flaws there that you don't know, right? And it is uncertainty because when you have a different size of a flaw, either it's OD or it's ID, outside diameter, inner diameter, or it have different shapes. Your NDE signal or here MFL signal might be very similar. And how to differentiate that? You have to understand the uncertainties, then tackle that problem specifically. Other things is, we call it sample geometry. And you hopefully you'll have good knowledge of what type of pipe you're dealing with, right? But sometimes the pipe has some, let's say, diameter changes over distance. It might be changed over in service life that you don't know, and you have to bring some geometrical uncertainties there. The certain inspection device that you don't have a fully understanding of the device there, so which will also give you some uncertainties. Well, second uncertainty is operation uncertainty. Is Let's use the same example. Let's say I gonna start my ND measurement position uh, at different direction. I'm gonna have this in operating in a different mode, and also when I have a sensor, the sensor might not be. If I have a sensor array, the angle of the sensor to the pipe inner wall might not be always the same. Even if it's a single sensor that you don't fully know that the sensor orientation during its scanning. Liftoff variations, for example, you might have vibration during this operation that will change the distance between the sensor and the material. And also, for example, the electrical contacts which are randomly positioned on a cracked surface and so on. This will give you the operations uncertainty. The uncertainty is always the operation process. The third is the structural uncertainties. Well, this can easily model using equations to understand the physics. So, for example, you can understand that using, for example, the surface roughness model. Then you can have different structures to be considered. While pipeline the simple geometry, it's a cylindrical structure. But still, you may have, surface roughness problems. You may have a change of the structures. There you can define the associated uncertainty. But last is parametric uncertainties, right? And when you deal with this process, there are a lot of parameters that you don't have full understanding of it. For example, the state and constituent models parameters. For example, sometimes you have to deal with, well, not in MFL, but sometimes you have to deal with the relaxation, reaction, and transport properties there. So those are the four major uncertain categories of sources dealing with END problem. Well, you can see some of the terms here are not directly applied to specific NDE, and this is not no way close to a complete list of all the source of uncertainties. But as a lecture here, or for the students, when you're dealing with uncertainties, I would suggest you to start from here and look at different aspects of uncertainties and define the uncertainties well. Come up with a table. Well, you may say, okay, well, this is really a big table, a lot of things to consider. What you need to do next? Well, as an engineer, we always prioritize things, right? So what you need to do is try to prioritize your uncertainty sources and deal with the one is more important or actually affect your NDE outcomes the most. Well, there's a lot of experience associated with that, but still, if you quantify your uncertainties, then you can actually look at this from a more statistical way. So you can do everything more quantitatively. All right, so this is the slides I want to talk about to convey my concept. Okay, so with uncertainty quantification, now we can look at the reliability analysis. And the people like to talk about reliability analysis, although reliability engineering people has a big scope, a bigger scope than NDE people. But so let's look at NDE people's reliability analysis vision is, first of all, I have the quantification of the sources of uncertainty. The second step is I want to have a model of the system design and assessment criteria. Then understand the uncertainty propagation in each stage. Well, I define my table. So I have my random variable defined what need to be understand along the vertical axis. Remember the first plot I want to plot. So what are the random variables, physical variables there? What are the material properties there? What is the geometrics and what are the loading conditions? Everything can be modeled, although model is not perfect, but we can use a model-based approach to simplify each of them, right? The model is just a mathematical simplification. And you can use that model to not only generate physical outcomes, but also help you to understand the variability in your NDE response and eventually lead to a probability measure of a failure of a system. The following step is called sensitivity analysis. For NDE people or people dealing with measurement in general, we've done this a lot. We call it sensitivity analysis when we perturb the input a little bit and we try to see, okay, how that affect the output in terms of its sensitivity. So this is called sensitivity analysis. So you can incorporate this in the entire process and make this a complete, a complete loop that you will look at the input and output and how that sensitivity can change by change a little bit in each parameter. The second part is the methodology for UQ, what's available out there. So let's look at the data acquisition step. You've learned this in the first course by Professor Upa, that you can have different ND methods, UT, electromagnetic method, ET, radiographic, and magnetic particle testing, and so on. There are many more, right? We also discussed this in the morning today. You get signals, you get data, and you deal with signal processing. Okay, this is what we're doing in this course. We can do a lot of data processing, like noise reduction through resampling, filtering, windowing, denoising techniques, so on. And as I said in the morning, it's not my purpose to go over this. This is more generalized signal processing, and you can easily get that ideas for all types of applications. But the idea here is how we can deal with the real ND problem and understand the noise reduction and eventually lead to the uncertainty reduction. That's more important. We'll have also deal with feature extraction and selection. There will be a half-day lecture on that particularly. This is basically an optimization problem. Well, from that, then we try to explain the uncertainties in terms of the material properties of measurement and noise. And we noted that I list noise separately. It's different from uncertainties, okay? So noise and uncertainties are different. Although that if you look at a measurement process, if you look at the equation I point out and say, okay, this is a noise term. You call this noise only because you have limited knowledge of what's going on there. Say, okay, this is noise, but noise itself is different from the uncertainties you are dealing with. And sometimes you can remove noise, but you can remove uncertainties, right? The second stage for UQ is in the diagnosis. So you can ensure the material structure quality and efficient process of NDE. So you can have qualitative model-based method, you can have quantitative model-based method to study, for example, qualitatively the cause-effect relationships. For quantitatively, you usually going to have a mathematical functions based on the physical knowledge to assess, for example, deterioration of material structure, and you can try to characterize discrete flaws. So there are literature out there you can read offline, but the takeaway here is, you have to use mathematical approach to quantitatively, and this is preferred when we do the quantification, that you want to have a quantitative approach. The third, highlight this as a machine learning based method. You can use machine learning to do the uncertain quantification. Well, there's still some debate going on there, but this is a tool that has been developed a lot, and it has improved the efficiency, and I will just highlight it here. So for machine learning, you can have supervised and supervised learning, just like we see in other applications. And you can use similar approaches to understand the uncertainties in the, for example, the model structure and model parameter. Here, the model is particularly the learning model you are dealing with. I highlight the common UQ techniques, so you can read this offline. I'm going to explain this briefly. You can divide them into Bayesian modeling approach or non-Bayesian modeling approach. For the Bayesian, you can have the Bayesian neural network as a very good candidate for uncertain quantification. So basically, you want to use this Bayesian neural network and try to understand the distribution of, for example, the of the parameters. Also, by assigning a probabilistic distribution of the weights of the neural network, you can also incorporate more UQ, flavor there. For non-Bayesian, a deep ensemble is a good way of doing it. And tomorrow's lecture, you will have a step-by-step hands-on experience or explanation on example where we use confidence measure as one application of uncertain quantification for the nuclear power plant problem. I'm sure you covered that physics in Professor Upa's course number 1. The third one is called Bayesian approximations. I highlight 3 techniques there with the literature. You can, of course, get that from me if you want to. When you have more time, I highly suggest you go over this if you're interested in, for example, the Monte Carlo dropout, Markov chain Monte Carlo, MCMC, and variational inference problems, where you can use that to get the uncertainties calculated. The third is the application that I work with several of my PhD students and postdoc, and so I can give you an explanation of how we can use the uncertain quantifications in some of the applications. Okay, during day 1, so you can start reading on this for the rest of this course. The first is using ambient magnetic backcast noise to study the early stage fatigue for stainless steel problem. This is a martensitic grade stainless steel used in turbine blades for power plant. And those are the samples which subject to different cyclic loadings and reach to a failure stage. The failure stage here is actually, it means that it develop a macro scale cracks. Before that, there's no crack observed, or there's no crack observed using conventional NDE techniques. Of course, if you look at the microscopic image, then you can see the microstructure changes, which is the indication or the precursor of macro scale defects. So we want to use NDE technique here, the MBN, to study the early stage fatigue. I don't know if you guys covered ambient in course number 1, or I need to briefly touch the physics of ambient? Could anybody let me know? Have you actually learned magnetic Barkhausen noise?
No, we didn't learn about this magnetic flux noise, ambient.
Okay. Okay. So let me then spend a few more minutes to explain this. I think this will be beneficial to understand the overall Euclid framework here. So magnetic Barkhausen noise, this is a technique which is under the category of micromagnetic method. It's an electromagnetic NDE method, as of course. And what you know, the physics behind that is you are going to introduce a AC excitation. Here, use the you can see the yoke here, which introduce the magnetic field variations in the material. So when you're dealing with ferromagnetic materials means you're going to have large mu. And the ferromagnetic materials, if you look at the microstructure, have magnetic domains. And if when you look at those magnetic domains at the microstructure level, when you apply a time varying magnetization to it, then a simply understanding of that is the magnetic domain, uh, each of them will have a magnetic moment, right? So with external magnetic field, those magnetic moment will try to align with the external fields. Well, if you change this in the AC way, then those magnetic domain was going to be oscillating due to that external AC fields. Well, when you have some microstructure features, for example, pinning site there or dislocation there, well, this will cause noise-like signal in your, your overall entire process when you have this magnetic domain wall changes versus the AC. So if you look at the measurement signal, or if you look at the BH curve there, you're gonna see those noise type signal on top of it when you do this, magnetization and demagnetization or magnetization in different orientation. So those noise signal is called magnetic Barkhausen noise. If you are in the acoustic domain, you can also have similar acoustic Barkhausen noise as well, but that's beyond the scope of this class. Well, in a nutshell, for magnetic Barkhausen noise, this is a micromagnetic measurement method that is sensitive to the microstructures nature of the material. For example, you can look at the dislocations, you can look at different precipitation, you can look at the different phases of the material when you are using this ambient technique. The downside, the disadvantage of the method is the randomness of it. First of all, sometimes it's very difficult to know the magnetic history or magnetization history of the material. Right? You don't know where it was. And also, its random nature, sometimes the repeatability, the reproducibility of the technique is poor. Okay, so that's a background. So I spent like 4 minutes explaining the physics of it. But let's look at the setup here. So we get the data measured from this sample. The sample is provided by Electric Power Research Institute, EPRI. And the sample is subject to a well-designed fatigue loading cycles. And we measure at the lever or this center part here where this will actually subject to the fatigue loading, and the crack will actually initiate from here based on the numerical FEM simulation. we get the ambient signal measured. Then we can extract the features in time and frequency domain. We do the principal component analysis study. We'll briefly explain that very soon in this course number 2. We can develop a probabilistic neural network and try to understand the fatigue life. Well, simply classify them into low, mid, or high fatigue stage. Low means, it can actually have a longer fatigue life or have more cycles to bear, and high fatigue, it means it's very close to failure. One definition of fatigue life percentage, we can define that as the cycles at failure when we observe the number of cycles, let's say they fail at 1 million cycles. Well, minus the cycles at NDE test, you may test this, let's say, at 200,000 cycles divided by cycles at failure. So in this case, your fatigue life is going to be 80%. 1 million minus 200,000 divided by 1 million, right? So which means you have 80% fatigue life here. So you'll see these results very soon, just showing you, then we can actually look at different features versus fatigue life. And this is based on principal component analysis. And I just showed the results very quickly that using this approach, that we can get the fatigue life estimated based on the ambient signals and its features extracted from it. Well, how to understand uncertainties there? One way of doing it is a well-known technique called ANOVA. If you take in statistics, that you'll see this is a very powerful tool, analysis of variance, that you can actually use that to measure the uncertainties. Particularly, you can have the repeatability and reproducibility of this measurement to quantify. And a simple implementation here is you can do repeated measurement, and by selecting a combination 4M, C4M measurements, you can calculate the standard deviation from those different combinations and calculate the standard deviation based on the sample data points here, and use that as your uncertainty measure. Well, another definition is you can have expanded uncertainty using the standard uncertainty defined based on standard deviation times K. Well, this K is actually depends on how you want to look at uncertainty. This K actually approximately equal to 2. Basically, it is what you see in under a normal or Gaussian distribution assumption. It should be actually 1.96, which give you a 95%. Right, it's a 95%. So when you have a plus minus 1.96 sigma, this is where the K comes from. Okay, so so you can calculate standard measure uncertainty. You expand that based on this 1.96 or approximately 2 coefficient. This is some results we got. You can get the expanded uncertainty versus repeated measurement for different signal features. And while this is a simple practice, but it's also very straightforward, and showing you the uncertainty will decrease over repeated measurement. Well, that's true, right? And this also shows you, more importantly, for different features, how the uncertainty changes over repeated measurement, right? And you can see how different features are sensitive to this EQ reduction approach. The second application is the convolutional neural network-based magnetic flux leakage inspection. So you can have ambient as your NDE method. Then you can use convolutional neural network CNN to understand the uncertainties for MFL. I'm sure you learned MFL before. Then for convolutional neural network, you can use that to understand the uncertainties associated with the MFL inspection. Okay, to study uncertainty from the forward approach first, you will start with different defect shapes. All those are artificial defect types. In the reality, you don't really know a well parameterized defects. But we start from those simple cubic, cylindrical, and also we defined, we call the C-shape type of defects, more realistic type of defect. Everything can be parameterized mathematically. This is important when we do the initial study of uncertainty quantification, so we can have all the parameters studied, and you can define the variational inference approach for the uncertainty quantification, where you will deal with the uncertainties either from data and also from model, or we call it rhetoric uncertainties and epistemic uncertainties. So you consider the data variation and also the model variation based on the measured signal. And you look at those two uncertainties with respect to the input parameters of NDE. So when you actually change the NDE parameters, here you have a well understood simulation model, and you can actually understand the uncertainties in data and then also in learning model. So this is the comparison of accuracy, average of total, aleatoric, and epistemic uncertainties for different parameters I just mentioned. So you can see for different parameters or different defect types here, you can calculate the associated uncertainty, and you can see the aleatoric uncertainty here is much, much higher than the epistemic uncertainty, right? So what does this tells me? First of all, my accuracy is negatively correlated with uncertainties, which can be tell from the first table that when I have increased uncertainties in my problem, my NDE accuracy will decrease. Okay, so this tells me that I can have a uncertainty quantification aspect to understand the NDE accuracy. And go back to Niraj's question is, when I have an NDE problem, I have a defect, I have an NDE measurement. I get my NDE measurement, I do an inversion, I try to estimate the defect size. Everything sounds very deterministic there, right? You have the data, you reconstruct. Well, actually, it's not. And its accuracy is associated with uncertainty. And how you define uncertainty? So if you define uncertainty well, then you can have a better probabilistic way of explaining your accuracy. Or when you look at a 95%, you know exactly where that 95% comes from in the context of uncertainties. Well, the second study from this CN-based MFL study is the main uncertainty comes from the defect size and shape, which is the aleatoric uncertainty. Okay, it's coming from where the intrinsic uncertainty of the flaws. Well, this is also good because you want the uncertainty associated with that, and you can use the uncertainty to better understanding the defect size and shape. Well, for the model-related uncertainty, it's relatively small. But still, it has uncertainty there, contributing to your final accuracy. Well, you can also use Bayesian neural network and deep ensembles to study the uncertainty. This is ongoing work. We haven't, the manuscript is on the preparation. We published several conference papers on this, that we try to introduce different uncertainties, for example, velocity variation and lift-off variations there, and we can, using simulation and experiment approach, to study the uncertainty. So when you're doing your own NDE experimental study or simulation study of uncertainties, pick several parameters or variance variabilities that you want to study, and that's what I said, prioritize. Then you can study the uncertainties associated with it, and eventually everything will be mapped to your NDE decision making, right? So this gave you a framework how you can deal with the uncertainties, although this is just one specific MFL application. How we can look at the uncertainties? Well, for example, you can look at the figure here. This shows the crack length versus number of cycles. Well, the crack length will increase over a number of cycles when we look at the fatigue cycles, but you can clearly see the uncertainty associated with it, right? The variations here, the different, when you actually have 68 samples here, from the observation, you can see the variations there is large. Well, how can I say this is large or small? We have to understand this through a UQ. And there are two types of randomness regarding the crack propagation here that you can observe. One is the global scattering of the curve. Although the shapes are similar, but you have a variability there for the crack length over cycles. Well, you also have a local irregularity, which show that the successive increments of the crack size along a given trajectory are also random in this case, right? So using a very classical Paris law approach, that the dAdn can be easily explained using this Paris law or power law here. Well, delta K is the concentration, stress concentration factor, while C and M are the parameters of this model to be estimated. Well, instead of having a deterministic C and M from this scattered measurement, now you should think about a distribution of C and M, right? Different way of doing it is you can have, an average of this and you can calculate the C and M, but it's better to associate uncertainty and explain that using the distribution of C and M here. So Bayesian updating algorithms allow us to update the knowledge with associated uncertainties here, or the distribution of the parameters here, and which can better explain this physical process. And here is a fatigue problem. So let's revisit the source of uncertainties. Well, I have a table before, right? Well, this tree diagram is not better in terms of a number of texts here, but I think it's better for us to now look at this again based on some examples we just visited. You can have intramodel uncertainties, you can have intermodal uncertainties. And based on what we just studied, you can look at different parameters. You are setting up your experimental simulation. Well, two other things there. For example, you can have human intervention and judgment. And that's bring uncertainties to our measurement and how we can actually develop the automation for detection, identification, and classification. How we can actually use learning to have a more efficient UQ. That's a third block here. The last is the undersampling based fast, efficient defect detection schemes instead of prolonged scans. How we can get less data, undersampling strategy, and I have an example following, which we called Kriging-based method to show that we can do that for UQ as well as better characterization of NDE. I have a couple of slides left, which I'm gonna finish in 15 minutes. So we have 30 minutes to go over the lab sessions. I would like to take I will take a 1-minute break here if there are any questions on the UQ, because I will now shift the gear a little bit, try to move to the uncertainty reduction, not just quantification, but reduce uncertainties with data fusion. In course number 1, I believe data fusion was briefly discussed. What is data fusion? And we will look at that through examples in this class. We'll have multiple lectures talk about data fusion. And I'm a strong believer of multi-modality NDE data fusion. And multi-modality not only means different physics, but also, let's say, same physics with different parameters. For example, electromagnetic method with different frequencies. That also can be a good way of doing multi-modality data fusion. So let's take maybe 1-minute break here. Any questions?
Any questions from online participants?
Okay, if no, let's continue. Okay, so how we can use data fusion to reduce uncertainties? Well, we have different methods. We have corresponding measurement from different methods here, right? F, you can get images from different methods. Well, how we can look at those images? We can look at them in the image space. We can look at them also in the feature space. Well, image space means that, for example, in the actual physical space, well, feature space, you can extract features from it by either performing transformation of the data. For example, you can use cosine transform, Fourier transform, wavelet transform, and so on. Of course, you can have other feature extraction techniques by looking at the defect or damage sensitive features. You can do registration of the image from different methods. You can also do feature registration from different methods. Well, you have uncertainty associated with each of them. Well, for different methods, the uncertainties sources can be different, right? As we explained before. And the quantification of that, the method can be same, can also be different. But how we can understand uncertainty among all methods, that's unknown. But hopefully that we can do some form of data fusion. Well, I list a few methods here developed by my students. For example, GAN, generalized additive models, wavelet-based decomposition. That's a transformation-based approach. Cross bilateral filter CBF, complementary sparse representation CSR, or deep learning. You can also use deep learning approach to the fusion. If we can accomplish data fusion, although we haven't actually looked at each of them in detail, that you can have a fused image or fused features, or you can also make this into a heterogeneous fusion that you can combine both image and features in the data fusion approach. Of course, you need different performance metrics to look at your performance of fusion, and this performance metrics has to be UQ oriented. So you need to look at the uncertainties in it. So it will try to not only show the reduction of uncertainty, but also give a matrix that can measure the performance of the data fusion. Before I move forward about data fusion example, another thing I want to point out is there are two branches here. One is called image fusion, the other is called information fusion. That's different concepts. Image fusion, well, I believe this is the fusion technique that we see or think most of the time, that you can fuse two image data at the pixel level, attribute level, even decision level. Sometimes, you need to incorporate expert level knowledge or information. For example, by voting or by Dempster-Shaffer theory. Well, for image fusion, I think this is easy to understand. But more importantly, I would like to, explain more in the information fusion. Well, instead of looking at the image, that more importantly is the information associated with it. Step back, maybe a side topic. I don't know if everybody agree with me. I think this is the concept I want to introduce in data processing 101 is data or image here is different from information, right? That's two different concepts. You may have a lot of data, but with very little information or zero information. Let me give you an example. You are recording a data from an SHM monitoring problem, right? You're monitoring a behavior of a bridge, and all the data remains to be constant over 10 years. What does that mean? You have a gigantic amount of data. If you save the data even periodically, you're going to have a lot of data, right? But information is very little. The information tells you there's nothing much changes over 10 years span. And the information is quite simple, right? And you can also have a small amount of data, but a lot of information embedded into it, right? So information theory people will have different way of looking at that. They have like entropy or different way of looking at the information in it. But for ND people, I want to make it very clear to you that the image data, or not necessarily image, but data is different from information. Okay, so if we're looking at information fusion, I think that's more important for NDE people, that you are actually looking at useful information in the data. And sometimes I like to call information is a subset of data or embedded in the data. Some people may disagree with me, but I think from the beginning, I prefer to consider information is a subset of data if you look at a set theory, right? And you can have a lot of data, but no information, or information is actually extracted from the data. Okay, is that clear? If that's clear, let's move forward. So we will have the information fusion probe here. For the method behind that, you can read published papers on, for example, cross bilateral filter approach here. So we use CBF to do the data fusion of eddy current MFL. Just show you a few examples here. For the same defect, we can have eddy current measurement, we can have MFL measurement. They are interestingly different, have different information out of it. And you can use data fusion technique. Here is CBF to get the similarity and geometric closeness um, of those pixels of images and try to fuse them using CBF and get a fuse image, which maximize information in your data. And the second image here show that for different parameters, here the parameter liftoff changes with smaller liftoff and large liftoff for capacitive measurement, how we can fuse them together by considering different parameters on certain contributors there. Okay, so we can also use wavelet. I don't know how many of you are familiar with wavelet. Well, this is just a time frequency analysis tool that similar, maybe not. No, I'm not gonna say similar, but it's not a transformation just like Fourier transform, cosine transform, and so on. You can look at this in a time frequency domain. And you can use data fusion based on wavelet transform by fuse the coefficients, then reconstruct the data. So you can have DWT, then you can have IDWT to get the fuse images. But the takeaway here is you use forward problem to get the data. You use data fusion technique at different level, and you are going to use those fusion examples, try to quantify the uncertainties. When you look at that fuse data, it should demonstrate that there's a reduction of uncertainty values by providing different metrics, which I'll show you very soon. There are two more examples using CSR and deep learning. Some of them has not been published, but I just want to show you different architecture here that you can play with the NDE data and using different approach to fuse them. A lot of math behind it, but you can use that to understand the uncertainties and the reduction of uncertainties using this data fusion assistance. Some examples shown here are the the metrics for different different practice of uncertainty estimation, and from this right figure here, what I want to show you here is the undersampling approach. That how about we reduce the data we collected with a ratio of 1:1. This means we have all the data, and a 10:1, which means I only have a 10% of the data, and how I can do the data reconstruction based on the undersampling method. The kriging is, simply speaking, is just an interpolation method, and based on the spatial arrangement of empirical observations. So you can use this kriging approach and try to deal with undersampling data set. And sometimes undersampling data set is preferred. Why is that? When we're doing the NDE, SHM, sometimes it's very costly to sample every data point, either in time domain or in spatial domain. So if we can actually reduce that sampling rate while still maintain a good quality of reconstruction by understanding the uncertainty there, this is important. Well, for this particular method, you may hear or learn or know some other methods in the domain. Starting from 2006, there's a way, the method called compressed sensing or compressive sensing, right? Well, this is beyond the scope of this NDE course. That's mathematical, how to say that, mathematical way of looking at undersampled data when you have prior knowledge considered. There are still some debates there. Some mathematicians think that compressed sensing is a hoax. That's not bring a lot of novelties here. I don't gonna bring my own judgment here. I'd rather you to spend more time reading it. But I think mathematically it's sound, and well, we have similar concepts here, although we are doing this differently. But for compressed sensing, that is how you can randomly sample the data at a much lower sampling rate, smaller than the Nyquist sampling rate, and still get a good reconstruction of the data. Particularly use L1 norm approach there. But for our method here, we use Kriging interpolation, and with Johnson estimation framework, we can actually downsample the data and show good reconstruction in the application. So that's something. So from the lecture, I would like to present as much material as possible. I know for 4-hour lecture for one topic, it's impossible to cover everything. There's a lot of reading materials that you can study, not just within this 5-day span. You can actually have a lot of things to read after this, and I hope that you can always contact me if you have any questions. I'll be very happy to answer that questions for you. So you have my email address here. Well, with that, this is the conclusion of our first day lecture. This is basically introduction of inverse problem and data processing. And data processing, we cover the uncertainty quantification for it. And we also touch briefly about some concept in data processing. You've seen something about feature selection, something about reconstruction, data fusion, and so on. And we will look at more examples and along the way. So I have 30 minutes here. I would like to spend some time on the lab assignments. We will have our lecture in the lab discussion for the first 3 days. And for the last 2 days, Professor Rao can help me to facilitate lab assignments and lab time for day 4 and day 5. Basically, I expect you guys spend more time on working on my lab assignments. And last 2 days, so 2 hours, it can be a group study. And I encourage you guys to work in group, small group, not one group for the entire class, but maybe 2-3 people can form a group and try to work on the lab assignments. That's perfectly fine with me. You guys can form a group at your will. I have not do that. So day 4, day 5, I expect you work on the lab and spend some time discussion. So Professor Rao can help me to facilitate that. Okay. Any question before I move to lab session?
Any questions from online participants before we proceed for the lab session? I don't see any. So we'll move to the lab session.
Okay. I hope everybody's still awake like I do. It's like 5:30 a.m. here in the morning. Okay. All right. So for the lab session, I have 2 lab sessions so far. I may have a third one. But let's see if we can handle all 3 of them. But I definitely want to do the lab 1 and lab 2. So 30 minutes here, I'm going to go over lab 1. I don't think I have time to go over lab session 2. But lab session 2 is a more like a scientific writing or literature review. Professor Rao can help me to distribute the materials. I think he has that, can distribute to everyone. So you can go over that and start reading and prepare for it. And hopefully you can submit the lab reports to me by end of this class. So the first lab is called Data Reconstruction Lab, and we're gonna pick the EIT. We are not going to talk about this EIT in our normal lecture hours, but I'm going to go in the lab briefly. And you will have a lab assignment given here. It's a simple, maybe I should not say simple here because we actually haven't actually worked on it. So, but I would say this is a simple in terms of problem itself. It's not a complex object to reconstruct. You only have two materials here, omega 1 and omega 2, where omega 1 centered at the origin with all the parameters given, particularly sigma there. Omega 2 centered at 0.20 with a diameter given, and the sigma is 0, non-conducting. You can treat it as air. And I hope you can use an 8-electrode EIT model to reconstruct the omega 2 inclusion there. So think about this is more like a infinite long cylindrical object. You can start with a 2D, right? 2D model. So the direction along the z-axis or the axis into the string is infinite. And if you have time, you can extend this to more electrodes. And even you can have smaller electrodes to see the performance of it, reconstruction. Read the lab materials, page 3 to page 19 of this slide. I suggest use MATLAB if you want to use other codes, other programming language, Python, C, it's up to you. But you'll have a very nice package and tutorial from the Manchester web page that I highly suggest. It's open source MATLAB codes. You can download that and submit the data and MATLAB codes with a short report with reconstruction results to Professor Rao, and Professor Rao will collect that and maybe pass it to me. The deadline is 25th. What's the local time there? It's 23rd, right? It's 23rd there.
Yeah, it's 16:08 right now.
Yeah, so you'll have a little bit more than 48 hours to complete this. If you need extension, let me know. I'll be very happy to give extension, okay? But this is just like a homework for today. So background for EIT, this is the lower right corner here is one illustration of EIT, and this is also related to your lab. So you have the excitation, you have your receiver, right? And of course, you will change the excitation and receiver pair accordingly. So you can have a current source excitation, then you can measure the voltage from other electrodes. And by doing that, by considering all the pairs of excitation receiver, then you can get all the measurement and try to reconstruct the inclusion here. And this picture clearly shows the medical application for EIT, and EIT has been widely applied to all areas, including medicine, NDE, and more. So we want to recover the conductivity or the permittivity of the interior of a body. It can be a human body, it can be an material for NDE applications from a knowledge of currents and voltage. In industry applications, this is called ERT or ECT as well. If you look at the resistance or the capacitance, basically you are trying to reconstruct the material properties of this object, either in conductivity or permittivity or impedance. And it applies small alternating currents at a single frequency, or you can also use multiple frequencies, and you can go to that website, look into it, right? I will not cover this in details. I think this is, as supposed to be a lab session. So I will, go to the website, and then I will come back to this very soon. Okay. Let me go to lab, website, and we'll come back to this mathematical model where you can have these simple differential equations to simulate this effect. But for the website there, you just need to know the background. I don't think you need to simulate this and develop everything from scratch. The website is called EDOS, which is the Electric Impedance and Diffuse Optical Tomography Reconstruction Software. And you only need to look at the electrical impedance reconstruction there. And I have that website opened. Let me go to that website. I hope everybody can see my screen here. All right.
Yes,
So
we can see
this
it.
very good. So you have the link there, and you can also Google EIDORS. This is open source software in MATLAB with very good tutorial. You can have the tutorial here, give you the basis of it. It also have, different way of, doing reconstruction, the concept of that, and you have the codes you can run directly using MATLAB. Okay, so I think this is a good starting point for you to do with for a 5-day workshop. So you don't have to start from scratch. It also have modeling there. Have different applications, right? You can see, for example, the line images and so on. So I would like you to explore this as a lab session for this class. And everything here is going to be way more complicated than the lab assignment I gave you. So that's why I expect you to start from here and try to do what I asked you to do for a simple omega 1, omega 2 inclusion problem, right? All right, I will leave this to you. Let me go back to my sharing of my slides. Any questions?
Yeah, actually, out of curiosity, I was just thinking that while say, analyzing the defects for any material, let it be a conductive material or with high conductivity or a behavior of a dielectric, but they all depend upon the frequency that we are using for measurement.
That's right.
Yeah, I mean to say that any material may behave like a
So
conductor or a dielectric.
are you
Depend.
asking this?
Yeah. So I mean to say that how do we incorporate that this loss tangent value, because the ratio of the conductivity and the dielectric behavior comes out to be loss tangent. So how to incorporate that, because that material will behave differently at different frequencies.
That's right. This is a very good question. Let's assume that the material properties is the same. I totally understand. This is definitely true if we look at for some materials for a wide frequency span. But let's start from simple problems here. So if you're asking about, um, for this particular lab project, that let's assume that the material property is the same for for frequency span, but of course we have to be realistic about what frequency we're using here. Um, but just let's assume it's not going to change over frequency. Otherwise, it could be really complicated at this stage. Well, for real problems, this is absolutely right. That for different frequencies, the material is going to behave or look differently. Well, for in that case, we probably gonna look at, we will see that more in other in future study when we talk about dispersion and other applications. But when we have that, we're gonna explicitly mention it. But yeah, this is a good question. But let's just assume it's constant. How about that?
Yeah, actually, that came into my mind because a few days ago we were discussing with ma'am about Srijan's thesis.
Right.
So he was doing with using some metamaterial lens. So that thing we observed, or you can say that really struck me right now that if we are using at a high frequency, that we are going for a gigahertz range, so then the material may behave differently. So that was the you can say that discussion led us to have this doubt.
Yeah. For his thesis work, I think that's only demonstrated. It's a very it's preliminary study, and I don't know if you see all of his thesis, um, but it's only work for some particular frequencies, right? It's used that material structure to focus the energy at some particular frequency. I don't think that will work for a wideband signal. But definitely, frequency dependent, that's something that we should consider.
Yeah.
Okay. Yeah, let me try to finish this lab session. I still have like 10 minutes. So there's a lot of reading materials here for to read. This is not my normal course material, so I just leave this to you for this reading, and start with this simple MATLAB, and you'll have some feeling of data reconstruction using MATLAB. Well, for lab session number 2, this is something that I hope that you can submit some writing by end of this 5-day course, is go over the non-iterative methods for low-frequency electromagnetic imaging. This is also a thesis coming out of our group, where we develop a novel monotonicity method for eddy current imaging, using non-iterative method that you'll see the details here. All the formulation, everything will be here. But I would like you to write a short report, 5 to 8 page report. Font size 12. I think single space is better. If it is double space, probably it'll be more than 8 pages. So I hope you can start collecting your literature on iterative and non-iterative methods for the imaging and sensing. If you have difficulty finding them, anytime send me email. I'll be very happy to direct you to some literature. But I would like you to do this practice. The reason for doing this is you'll have a better understanding of a wide variety of the image and sensing applications out there. So it's good to do that through a lab session. The second is I want you to classify them into non-iterative and iterative methods. You don't have to reproduce the results there, but I want to at least understand what's out there for those two categories. Well, for non-iterative, this is a recent progress of non-iterative methods that you can read. And of course, there are several papers out there you can cite from Professor Tamperino and also from another student from our group. So you can read it. And this is new methods being developed just last a few years ago. So I'd rather you read this paper for non-iterative NDE reconstruction. Okay, so that's the second lab session, and you see that for the second lab session, I already give you a lot of reading materials from these slides, and you can have more details from the published paper out there. And I expect that paper will be probably in one of your review articles there. Okay, so that's lab session number 2. We will keep talking about labs and answer questions on lab, in day 2 and day 3. I expect to spend afternoon sessions on covering lecture materials, and when we have some lab session, questions, we can also cover that. Okay, so that's a plan. Um, any questions on the lab session? And I think you can start right away on the lab session number 1 after today. We'll start with the lecture notes, then download the codes, try to form the problem in MATLAB, and simulate and try to get some data and do the reconstruction there. Right, and if you have the results, you're very welcome to share your screen and discuss in front of the class in day 2, day 3. Okay, so that's the lab session. Before you go, I want to give you a yes.
Yeah, we have one question from the audience here. 1 minute.
Okay.
Yeah, here
You come this side.
in the ND imaging, how to differentiate between uncertainty and noise.
Okay, very good. So this is something that we discussed, and I'm glad you asked this question again. Let's go back to my slides and let me try to answer your question from my slides. And I think it's perfect to start with this slides. Okay, can you see my slides?
Yes.
Yeah. So uncertainty and noise are complete 2 different things. Hopefully, after this lecture, that we will not, exchange those 2 terms together. Well, uncertainty, you can see it comes from different aspects of when we do NDE and the entire NDE process. It is associated with, for example, from the material level, the randomness of the material. For example, some material has its randomness in the, let's say, grain structure. It has its randomness when we dealing with, for example, the NBN, when we have those precipitates or different phases of a material in it, different dislocation density there. That's something will contribute to the uncertainty of our measurement. But you cannot call that noise, right? The noise is complete randomness that most of the time that you don't, you get that because of sometimes it's careless or some mistakes or errors. But uncertainty at that level, material level, is intrinsic to the material itself. And it's always in your measurement that you have to quantify and understand. Well, in a sense, noise in that case, for example, because of the instrument, let's say the instrument performance, the drifting due to the temperature variations of the measurement environment, go to the electronics components, or go to the temperature variation, go to the pressure variation. So those kind of noise is more randomness in the signal itself. And those randomness can be reduced by simple signal averaging, right? This is people usually do. When you have a noise in the signal, in the ND signal, you can take multiple measurement and reduce that noise. But some intrinsic randomness, what I just mentioned, contribute to uncertainty due to the material randomness. You will never remove it. It's always there. That's the uncertainty we have to deal with in NDE. While some other uncertainties, it's also not called noise. For example, the operational uncertainties that I have, something that I don't know when I adopt some instrumentation, when do some operation that I don't really know, but it's not in its noise form. I cannot call it noise, but that's something, if I have a better knowledge in operation condition, then I can reduce it, right? And I'd rather not call it noise. Other things, for example, structural uncertainty, when we talk about, let's say, surface variations due to liftoff or the surface preparation, then it will affect our signals. The confusion comes from you. I totally understand that. Before that, if we don't understand uncertainties, you think everything gonna be a noise, right? You have whatever you want to measure, that's A of F, and you have a noise term plus N. People tend to combine everything into that N term, and you'll see people try to use a Gaussian to describe a noise. Remember, I think even I did when I was a student, right? I have a signal and I add some noise to it. I add a Gaussian noise to it, right? Can I do it? Have you asked yourself when people add a lot of additive Gaussian noise to it? Is that correct? Well, people say, oh, okay, this is a fairly good assumption, right? No, I don't think so, right? If you understand uncertainties, probably you're going to be hesitated to do that because not everything going to be Gaussian. And you cannot call that a noise term anymore, right? Instead of calling it a noise term, you probably should look at that into different uncertainty contributions. And some of them are noise, but some of them not. So this is an explanation of the difference between uncertainty and noise. And this is a high-level explanation. I believe I convince you they are different. But for specific ND problems, then you can actually look at it into more depth and detail. And you have a better understanding what noise is and what uncertainties are. Hopefully I answer your question.
Yeah, thank you. I have one more question.
Yes.
In microwave, I'm doing one problem, material characterization. Here, for material characterization of dielectric materials, uh, how can I use this? How can I create the data for material characterization?
Okay. Let me try to understand your question first. How to gather data for material
Yes,
characterization?
yes.
For microwave, there are different ways of doing material characterization. There are different approaches. For example, one simple approach you can use, let's say, waveguide approach. You can put the material in a waveguide, and you can estimate the material properties of it. You can also have an open-ended waveguide. You can put the material there. You can have some slab of material. You can measure it. You can measure the transmission or reflection of it, right? If I understand the question correctly, is well, you first have to have some assumptions and ask yourself what kind of material properties you want to measure, and then you try to remove the other confounding things and design your material samples accordingly and your micro measurement setup accordingly. That you're going to choose the right way to do it. Then that's how you get your data. And if you can tell me more about what kind of material property or what kind of material characteristics you're trying to
It's like electrical
evaluate.
properties, permittivity and loss factor of the material.
Okay, then I think the simple waveguide approach probably gonna work.
Yes,
You
I
don't
am
really
using.
care about.
Yes, I am using by using the waveguide approach only. But right now we are using comparing this measured signal with analytical equations. It's like a optimization iterative technique. But here can we use can we create a data and we can use like ML and this deep learning algorithms to get properties.
Yeah, of course you can. There should be publication out there. I'm not 100% sure the recent publications, but definitely you can use machine learning to do the material characterization. There are not a lot of out there for NDE problem, but of course you can. The key thing there is you should have, if you want to do deep learning here, maybe not just deep learning, just machine learning, you have to have a very good training data set to do it. How are you going to do it? Are you going to generate a data set using simulation, or you are going to have good data set from your experiment? But they're going to be expensive, and you have limited data set there.
Yes.
And your purpose of this material characterization, is that going to be like when you have a new material coming in, you want to do the actually become a regression problem. You want to predict what kind of material properties they're going to be when you have a new material coming in using deep learning. Is that what you're trying to do? Or you want to use deep learning to give you a better estimation of the material properties?
Yeah, better estimation of the material properties.
Okay. So in that case, I think, of course, that's definitely possible, and you can use starting from simulation data set to do that. And try to get your data. If I understand that, you can start from simulation, get your data set. Well, you use hybrid simulation plus experimental data set. Assume your experiment data is good. Then you can train your model to do it. Well, what kind of model? That's a question there that you can spend more time thinking about it.
Yes.
And that's definitely doable. I think that's definitely doable, and I believe people have done that. I haven't done particularly for micromaterial characterization using deep learning, but for other problem I'm working on, definitely I think it's possible.
Thank you.
Yeah, give it a try. Then you can always email me if you have any results we discuss. That's perfectly fine.
Yeah, sure. Thank you.
Yeah. Okay. Any other question?
Yeah, I'll just check. I don't see anything in chat. I'll just ask any questions from the online participants. Okay. Then we'll stop here today.
Very good.
Yeah.
So I'll see you guys tomorrow, and hopefully you can have some time to go over the lab session and start reading.
Yeah. So thanks a lot.
Yeah, no problem. So I'll see you guys tomorrow, and I will try to get some sleep then.
Hope you too get some sleep.
Yeah.
Yeah.
See you guys tomorrow.
Yeah.
Bye bye.